Welcome to my channel. I've made some online recordings for the course Reasoning and Argumentation, and this is a review session that covers the formal exercises we've been doing the past 5-6 weeks. I'm here ensconced in my tropical outpost. It's nice and warm, the waves are crashing into the beach. And that whenever that's the case, it makes me want to do some logic and decision theory and probability theory and set theory. So let's do a quick review. And I'm not sure how long this video will be, maybe 45 minutes, maybe longer. And I'll do some exercises and explain the central concepts from all those different topics again. So the overview, we will cover set theory, relations and functions, correspondences, propositional logic, predicate logic, and then probability theory, which you can't see because I'm in front of it. And for each of these topics, I will go over the central concepts and do some explaining. So, clearly, the central concept in set theory is that of a set, and by now you'll be used to the convention of writing a set by listing its members enclosed in curly brackets. So here we have the set containing the elements 1 and 2 and 3. We can also give this set the name A, and then we could ask, is 2 a member of A? And the answer is yes, it is. It's in there. And we can also make the statement 4 is not a member of A. And this is also correct because 4 is not an element of set A. I can also write this set down in another way. I could say the set containing all the x's such that, vertical line, x is an element of the natural numbers and x is less than 4. This is an alternative name for the very same set A, aka the set containing 1, 2, and 3. The thing about sets is that they're individuated based on their members, meaning two sets are the same if and only if they have the same members. This is sometimes called the Axiom of Extensionality. With sets, what's important is what's in them, not what they're called. So then we have the subset relation and the superset relation. Well, that's pretty straightforward. For instance, the set containing 1 and 2 is a subset of the set containing 1 and 2 and 3. Because all the members that are in the former are also in the latter. The set 1 and 2 and 3 is also a subset of itself, because all the members that are in the former are also in the latter. But it is not a proper subset of 1 and 2 and 3. But the set 1 and 2 is a proper subset of the set 1 and 2 and 3. Because all the members in the former are in the latter, and some elements in the latter are not in the former. And when it comes to superset, we have the same concepts: proper superset and superset. Okay, now let's talk about union and intersection. So suppose I take the set 1 and 2 and 3 again, and I want to know the intersection with the set 2 and 3 and 4. Well, the result of this operation is a new set, namely the set containing all the members that are in both. So we have number 2 and number 3. If I were to take the union of these two sets, then I would get the set containing all the elements that are in either. That would be 1, 2, 3, and 4, because those numbers are or in the one, or in the other, or in both. Clearly, you don't have to put 2 and 3 in there twice, because again, sets care about what's in them, and if you write down a number twice, it's either in there or it's not. It cannot be in there twice. So you can already see that the notion of intersection corresponds to the logical operation of AND, which I'll come back to later, whereas the set theoretic operation of union corresponds to the logical OR. 1, 2, and 3, and 4 are those elements that are in the one or in the other. And 2 and 3 are those elements that are in the one and in the other. Okay, then we have the complement. The complement of a set X is basically all the elements that are not in X. Elements not in X. Now, usually you have to know the domain when you take the complement. So let's say the domain of a particular question is 1 through 10, and set A is the set containing 1, 2, 3, and 4, then the complement of A relative to this domain is 6, 7, 8, 9, and 10. All those elements that are not in A. And the complement, we use a horizontal line on top of the name of the set of which you take the complement. We also saw some questions like, suppose we take the intersection of X and Y, take the complement of that. Is that the same as the complement of X union the complement of Y? Well, with questions like this, it's usually useful to draw Venn diagrams. And we know what they look like. So let's draw the Venn diagram of X, the Venn diagram of Y, and first we take the intersection of those two, which is this little area there, and now we want to know the complement of this particular little area. So the complement of the little area is everything except that little area. So that is the complement of the intersection of X and Y. Now let's see if that's the same as the union of the complement of X and the complement of Y. So first we draw X again, and we take the complement of X. Okay. So far so good. Now we draw Y, and we take the complement of Y, and we get the complement, and now we take the union of those two. Well, there's a little bit of overlap we saw. So what we'll end up with is everything shaded except for the particular little area that is not shaded in either this or that, which is exactly the same as we saw in the previous situation. So the answer is yes, this is true. And you can check that the best by drawing Venn diagrams and then shading the different areas. Next up we have the power set, which we draw with a curly P and we apply it to a set. Now the power set of A is all the subset, the set of all the subsets of A. The set of all the subsets of A. So let's say that A is 1 and 2, the set containing 1 and 2. And now we want to know what is the power set of A. Well, it's a set. Okay, so we draw a curly bracket open. And we start with the empty set, which is a 0 with a line through it. The empty set is a subset of every set. Why is the empty set a subset of every set? Because the subset, everything in the subset is such that if it's in there, it's in the set in question. It's vacuously a subset of everything. Well, A itself is also in the power set of A, because A is a subset of itself. The set containing 1 is a subset of A, and the set containing 2 is a subset of A. And that's it. You know, we don't have to add the set 2 and 1, because that's the same as set A itself. You know, the order in which you write down the elements is not important. So we have 1, 2, 3, 4 elements in the power set of A. And it turns out that whenever A has size n, the power set of A has size 2 to the power of n. Okay. So in this case 4, if A had 3 members, the power set would have had 8 members, because 2 to the third is 8. Alright, so that's very quickly what the power set is. So cardinality, well, I just talked about it. You know, the cardinality of A can be a number n, and we just said that the power set of A in that case is then 2 to the power of n. Sorry, so the cardinality of a set is simply the number of elements, and you write it down with vertical lines on both sides of the set, of the name of the set in question. Okay, so then we have the Cartesian product of two sets. This is basically a set of ordered pairs. So let me take an example. So suppose A equals 1 and 2, and B is left, center, and right. Right. Okay. Now the Cartesian product, which we write with a multiply sign, is the set of all ordered pairs such that the first member of the ordered pair in question is a member of A, and the second member is one of B. So we have one left, one center, and one right. Comma, and we have two left, two center, and two right. Curly brackets closed. So we have 6 elements in the Cartesian product of these two sets, which again the multiply sign gives it away. The cardinality of A equals B is the same as the cardinality of A multiplied by the cardinality of B. Now these are ordered pairs, and ordered pairs are different from sets. the name says it already, with an ordered pair, the order matters. So when you have an ordered pair, you write that over. So if you have an ordered pair, or if you have two ordered pairs, and one is AB and the other one is XY, this is the case only if and only if A equals X and B equals Y. The order matters. So the ordered set AB is not the same as the ordered set BA, but the set AB is the same as the set BA. Okay. Now, I also wrote the words necessary and sufficient down there. I mean, these are not very complicated. Basically, suppose we have the set of animals and we have a subset of all the tigers. Then you could say that being, let's call that T, let's call this A. So being an element of A is sufficient for being an element of T, but not necessary, because that's the other way around. Being an element of T is sufficient for being an element of A, but not necessary, because you can be an A without being a T, like here or there or there. But being an element of A is necessary for being an element of T. Something cannot be in T without being in A. All right, so you can see that you can explain these notions of sufficient or enough and necessary, needed. You can explain those very easily using set theory and Venn diagrams. And these words will occur again and again in philosophy and logic, so it's handy to know those words. All right, let's do some exercises now. Here's a question. We have a set containing 7, 5, and the empty set. Is the empty set an element of that set? Well, let's look at the elements. 7, 5, empty set. So yeah, it's in there. The empty set is just a set. You can also write it with curly brackets and nothing in between. There's only one empty set. It is a member of this set. It's not a member of every set. For instance, the example we discussed earlier, 1, 2, 3, doesn't have the empty set as an element. Now right there we see the set of X such that X lives in Utrecht. All people or all entities that live in Utrecht. All right. So I don't even know how big is Utrecht, 300,000. So, and it includes animals as well, because it includes living things, perhaps even plants, who knows. Is the empty set a subset of that set? What do you think? Well, yes, it is, because the empty set is a subset of every set. For everything in the empty set, which is nothing, it holds that if it's in the empty set, it's in the set in question. It's vacuously a subset of every set. Now, if that strikes you as unintuitive, you can also just memorize it. Okay. Here we have some questions about Cartesian products and cardinalities. So we have A, 1 and 2 and 3, and B, round square. Well, the Cartesian product of B and A is round 1, round 2, round 3, square 1, square 2, square 3, and those are all ordered pairs in a set, and that is the Cartesian product. Now, if you want to know the cardinality of that, that's just 6. It's pretty straightforward. Okay, now we have B times C, and we subtract a number of elements. And I haven't explained the forward slash yet. If you have x forward slash y, that basically means, it basically means all the elements that are in x but not in y. So x forward slash y, elements in x but not in y. Okay. Well, B times C is going to be round up, round down, round left, round right, square up, square down, square left, square right. And they want us to subtract 3. So this is going to be a set with ordered pairs. Round up is still in there, round up. Round down is in there. Round left is not in there, but round right is in there. Square up is in there. Square down is not in there. Square left is in there. And square right is in there. And I made one mistake. Square up is not in there. So that's it. We have a set with 5 ordered pairs in it. 8 ordered pairs minus 3 equals 5. Well, this third question is we covered this in the homeworks, but it basically says that if you construct a new set of ordered pairs out of one set of ordered pairs already, and a new set, will that be different or the same as if you take the ordered pair where the first element is from A and the second element is from the Cartesian product of these two? And the answer is not the same. I mean, one reason is that the ordered pairs in the first this first set, they are ordered pairs where the first element is an ordered pair. But in the second case, they consist of ordered pairs where the second element is an ordered pair. So not the same. Okay, so I think these are the most important concepts when it comes to set theory. And on the exam, you'll get some basic questions about those. All right, so relations. I just talked about relations, in fact, already. Relations are sets of ordered pairs. So if you have A, B as an ordered pair, B, C as an ordered pair, A, C as an ordered pair, B, A as an ordered pair, A as an ordered pair, then this could be the extension of a certain relation. Let's call it R. Now, there's a number of interesting characteristics that you can ask about relations. Do they have this characteristic in question? The most important ones that we covered are: is the relation transitive? Is the relation symmetric? And is the relation reflexive? Now, when it comes to these questions, we have again to keep in mind the domain of the relation. So let's say that we have our domain is people, and a relation is being a daughter of. Then we can ask, is this relation transitive? Is it symmetric, or is it reflexive? Well, this particular one happens to be none. It's not transitive because if A is the daughter of B, and B is the daughter of C, that does definitely not entail that A is the daughter of C. So if we had the relation of being a descendant of, it would be transitive, because if A is a descendant of B, B is a descendant of C, that would mean that A is a descendant of C. Is it symmetric? Well, being a daughter of is not symmetric. If you are the daughter of your mother, then your mother is definitely not your daughter. Is it reflexive? Are you your own daughter? No. So this particular relation does not meet any of those characteristics. But some other relations do. Let's imagine two homes and they are neighbors of each other. A and B are neighbors. And then here we have C, D, and E, and these are neighbors, right? Or C is a neighbor of D and D is a neighbor of E. Well, that's symmetric. If R is being a neighbor of, then RAB holds, but RBA holds as well. RCD holds, and RDC holds as well, as because this is a symmetric relation. Is it transitive? Well, no, because C is a neighbor of D, D is a neighbor of E, but it's not true that C is a neighbor of E. Is it reflexive? Are you your own neighbor? No. Okay, then we have the inverse of a relation. So if we have the relation of being a daughter of, and A is the daughter of B, and B is the daughter of C, and D is a daughter of C, then the inverse is simply that same relation with the members of each ordered pair reversed. So it would then become BA, CB, and CD. So if being a daughter of what would be the inverse of that in English? Well, it's having as a daughter, to have as a daughter. Blank has as daughter blank. It's not beautiful English, but that's what it means, the inverse. Now, another thing about relations is that you can compose them. So suppose we have R, and R is being a neighbor of, right? AB, and BCD, CDE. All right, so A is a neighbor of B, and vice versa. Now you could ask, suppose we take the relation G, and that is the composite of R and R. So G relates those elements, all ordered pairs, R and G, when they are related to something by R, which is related to the second member of the ordered pair by R. So we could ask, does G hold between C and E? Well, it turns out that yes. Yeah, because C and D are related by R, and D and E are related by R, and G is nothing but the composite of R and itself. So G relates those ordered pairs that are such that the first member is related by R to something, and that something is related to E by R. So this is being a neighbor of a neighbor in this case. Being a neighbor of a neighbor. Now we just talked about is being a neighbor reflexive, and the answer is no. But maybe this is reflexive, because you are a neighbor of your neighbor, because being a neighbor is symmetric. Okay, so think about that. Then we have the notion of a function. Now this proved to be fairly difficult, so I'm gonna, on the exam, we will not ask difficult questions about functions. Basically, functions are a subset of all the relations. Functions are also ordered pairs, sets of ordered pairs. But they are a unique, they are a specific kind of ordered pair, namely ordered pairs that are never one too many. That are never one too many. And by I don't mean one too many, but one too many. Now, what does that word mean? One too many. Well, here I drew a set of ordered pairs. A, B, C, D, E, F, and AC. Now, as you can see, A is related to B, but A is also related to C. A is a member of an ordered pair where it's the first element. It matches up with B, and here it's a member of another ordered pair. It matches up with C. Now that would be one too many, because A is mapped onto and B and C, and that is never the case with functions. You know, in class I gave an example, right? So I have here we have people. Let's have three people. There's Annie and Bill and Krista. And here we have cities. And the city is, and these are cities. Let's take Athens, and Berlin, and Calcutta. All right, let's draw a little circle here and a circle there. All right, now let's draw the relation has visited. Well, maybe Annie has visited Athens. Maybe Annie has visited Berlin. And let's say that Bill has only visited Calcutta. And Krista has visited Calcutta. This is relation has visited. Well, this is not a function. Why? Well, because it's one to many. Annie is mapped onto Athens and Berlin. But if we take a different relation, let's say we take the relation is currently in, it's impossible to be in two places at the same time. So this line has got to go. So if we go to this situation, now it is a function, because you'll never have a line from the domain to the range that is taking one element from the domain and takes it to two elements in the range. Okay, so I think that's the important thing about functions. Then within those functions, so within relations that are never one-to-many, there are additional characteristics, and one of them is one-to-one. Well, one-to-one, the name already says it. Bill and Krista here are many-to-one, because Bill goes to Calcutta and Krista goes to Calcutta, is currently in. But if a function is one-to-one, then that will never happen. So we remove this line by Bill, and we say, okay, let's say Bill is in Berlin. Now this relation is one-to-one. Annie is in Athens, Bill is in Berlin, and Krista is in Calcutta. It's one-to-one. It's not many-to-one. Now the cool thing about this particular one, it's also onto, and onto means that all the elements in the range receive an arrow from this relation from the domain. So everything is covered by this particular relation. There are no uncovered cities. If Detroit was here, then the function would not be onto. But there is no Detroit there, so it is onto. And if a function is one-to-one and onto, it's both one-to-one and onto. And now it becomes a correspondence. And if two sets are such that there's a one-to-one correspondence between them, then they have the same cardinality. Because you can see here that if you need three people and you can't go one-to-many because it's a function, and you can't go many-to-one because it's one-to-one, and it's onto, so there are no uncovered dots here, then you can see that you need the same number of elements here and the number of elements there. Now, by the way, I have assumed that functions are complete. I have not included partial functions. Okay, so we will ignore partial functions and only look at complete functions. Okay, let's look at some exercises. All right, so let's go back to brothers and sisters. Well, is a brother of, is that reflexive? Are you your own brother? No. If you are a brother of your brother, are they your brother? No. I now see that it's not reflexive. Sorry, not symmetric. Because if you have a sister, right, and you are your sister's brother, but your sister is not your brother. So brother is symmetric when A and B are males, but not when they have different genders. Is it transitive? So if A is a brother of B and B is a brother of C, does that mean that A is a brother of C Well, it seems to me that it does, and I'm ignoring for the moment half-brothers and you know, all these complex familial situations. So it strikes me as transitive. If we only look at biological brothers, 100% biological brothers. Sharing an ancestor with a person, is that reflexive? Well, that's partly semantics, but I would say yes, it is reflexive, because sharing an ancestor is having the same ancestor and you have the same ancestor as you. Is it symmetric? Seems to me yes. Almost all relations involving identity having the same are symmetric. You know, if you have the same, if you make the same amount of money as someone else, then they make the same amount of money as you. That's got to be symmetric. Same thing with sharing an ancestor. And transitive also seems to me to be the case. It doesn't have to be the same ancestor, so you can be remotely connected with a person by ancestry, or you can have share an ancestor, and they might be remotely connected to a third person. Then there is some connection to you and this third person. All right, so yeah, I think we can move on. I think that the notions of symmetry, reflexivity, and transitivity are pretty clear by now. All right, so here we have some here a set A and a relation R on A. Now here we have the intersection applied to relations. So let's see how that works. So R is this particular relation, 6 ordered pairs, and it's intersected with the inverse of that same relation. Well, the inverse of that relation is simply every number flipped around. 1, 0, 1, 1, sorry, 0, 0, 4, 1, 0, 7, sorry, 7, 0, 4, 4, 4. All right, I'm a bad drawer. Let me start that over. So we got, we got 1, 0, 0, 0, 4, 1, 7, 0, 4, 4, 2, 4, curly bracket, curly bracket. So this is R minus 1. All right, now the intersection means elements that are in both. Well, which elements are in R and in the reverse, or the inverse, I should say? Well, only 0 and 0 and 4.4. So yeah, that's correct. The intersection of these two relations is 0.0 and 4,4. Here's a question about union. So suppose you have a relation and you combine that relation with its inverse. So let's say we have 2 and 3 and 5 and 7. All right. And then we take the inverse, which is 3, 2 and 7, 5. And now we put them together. So I'll just erase this curly bracket and that. Okay, now is this symmetric? Well, symmetric means that for every ordered pair in the relation, the reverse ordered pair is there too. And it is, because we just put it in. So the answer is yes. That is correct. And finally, what's so special about R union R minus 1 when R is symmetric? Well, if R is already symmetric, that means for every pair, the inverse is in it. So if you take the union of R and R minus 1, it's the same as R. So when R is symmetric, R union R minus 1 equals R. Nothing gets added by adding the reverse. All right, so I hope that was clear. So let's now move on to propositional logic, and we kept this fairly simple. We do no derivations. We do no very complex proofs. All we did was simple translations and identifying the main connective and coming up with truth tables and the difference between tautologies, contradictions, and contingent statements. Okay, so the building blocks in propositional logic are atomic sentences, and we use capital PQR, mostly P and Q. Now, these are atomic sentences. They are the smallest building blocks. But from those small building blocks, we can build complex sentences using truth functional connectives, sentential connectives, such as and, or, not, and the horseshoe. For instance, I can combine P and Q with an and. I can combine P and Q with an or. I can combine P and Q with the horseshoe. And I can put a not in front of P or Q. Now, whenever people build a logic, they talk about when is a sentence well formed. Well, these atomic letters, they are well formed. I can just write P and I'm not in violation of the rules of the grammar. And these are also well formed. So if I have two well formed formulas, here I have P and Q, and I combine them with an and, the result is also a well formed formula. The same applies to or, if then, and not. So this is what's known as a recursive definition of what a well formed formula is. I give you certain building blocks, and I give you a procedure for constructing more complex formulas. And as long as you stick to those procedures, you will stay within the domain of well-formedness. So for instance, we just saw that P horseshoe Q is well-formed and not Q is well-formed. So we can take those and put an and between them. So I can say P horseshoe Q and not Q. So I just combined two well-formed formulas with this connective, and the result is also well-formed. Now, this brings me to the important concept of the main connective. Whenever you see whenever you see a formula in propositional logic and also predicate logic, it's useful to ask yourself, what's the main connective? And the main connective is, well, if you were to break down this formula into its components, what was the last operation that they did to build this formula? If you were to rebuild it from the atoms, from the atomic sentences, what would be the last move? Well, the last move was the and. So and is the main connective. All right. So let me give you some examples and then ask you what the main connective is. So suppose I say not R and Q, horseshoe, not B, and not or are or are. Well, what is the main connective here? Well, it's maybe too easy, but it's the and. Look at the brackets. Now, of course, I could draw these brackets in some other way, and that would change what the main connective is. You know, if the brackets were let's see, Q arrow not P and not R. So if I write it like this, now the main connective would be the or. Again, you can look at the brackets and see how to disambiguate, or the brackets disambiguate this formula. Okay, so then the other thing we talked about was truth tables. And if you have a very simple formula, like for instance, not P, horseshoe Q, well, if you want to know what that says, you draw a truth table and you try to build this formula out of its components. All right, so here we go. I have to get not P here, and then here we can put P and Q. So I'm going to write down true, true, false, false, true, false, true, false. Now I've covered all the options, 2 to the power of 2. Now in this column for not P, I have to write down the truth value for not P in those circumstances. And there are 4 different circumstances. Every row corresponds to a circumstance, as it were. You could think of them as models. Well, not P, is that true or false if P is true? False. Is it true or false if P is true? Still false. Is it true or false if P is false? True. Is it true or false if P is false? True. So basically, not P has the inverse truth value from P. It's flipped around. Putting a not in front of it flips it around. Okay. Now here I have the horseshoe. And the truth table for the horseshoe, I could write it quickly here, is slightly counterintuitive according to most students, but it is TTFF, TFTF. The horseshoe is true always, except when you go from truth to falsehood. So it's only false in this particular case. It's true here and it's true there. This is not very well drawn. Let me try that again. A, B, A horseshoe B. All right, so we got T, T, F, F, T, F, T, F. The horseshoe is true when they're both true, the antecedent and the consequent. It is false when the antecedent is true and the consequent is false. It is true when the antecedent is false and the consequent true. And it is true when the antecedent is false and the consequent is false. All right, so we have to do the same thing here. Not P is our antecedent. Q is our consequent. All right, so antecedent false, consequent true. True. That's line 3 here. Antecedent false, consequent false. True. That's line 4 here. Antecedent true, consequent false. Aha, false. That's line 2 there. And finally, antecedent true, consequent false, false again. Sorry, that's wrong. I made a mistake. So it's antecedent true, consequent. I made a mistake in the last one. All right, ignore. Line 3 is from true to true, which is true, and line 4 is from true to false, which is false. So it's only false in line 4. All right. Now we can also make truth tables for more complicated sentences. For instance, if I say B, all right, let's say Q horseshoe B and not R. All right, well, that is 3 letters. So we have to somehow start with B, Q, R, and let's make a Q horseshoe P in there, and let's put not R in there for 2, 2, 2, something like that. And here we go. True, 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 false, 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 false. True, true, false, false. True, true, false, false. True, false, true, false, true, false, true, false. So this captures all the possibilities, 8 of them. 2 to the power of 3, where 3 is the number of atomic letters. Okay, now we first do Q horseshoe P. We want to build up step by step until we get here. All right, Q horseshoe P. All right, going from truth to truth, true. Going from truth to truth, true. Going from falsehood to truth, true. Going from falsehood to truth, true. Going from truth to falsehood, false. Going from truth to falsehood, false. Going from falsehood to falsehood, true, false, false, true. Not R, so we have to flip around R. Well, we got R here. Flipping is fairly simple. True becomes false, false becomes true, truth becomes false, false becomes true, true becomes false, false becomes true, true becomes false, false becomes true. And now we have to take the AND. Now what is the truth table of AND again? Well, very simple. A, B, A, and B. The truth table for AND is true, true, false, false, false. True, false, true, false. It is true when both are true and false otherwise. So the truth table for AND gets a true only on line 1. It gets a false in line 2 and 3 and 4. So we have a conjunction, and because an AND statement is also called a conjunction. And an OR statement is called a disjunction. We have a conjunction where the left conjunct is a horseshoe statement and the right conjunct is the negation of R. Well, luck has it they are right here. So we look at are the left-hand side and the right-hand side of this conjunction both true? And only then is the conjunction true. So here we have T and F. F. T and T. T. T and F. F. T and T. T. F and F. F. F and T, F, T and F, F, T and T, T. So we get true here, true there, and true there. That's how you build a truth table with sentences consisting of 3 atomic letters. Now, one more thing about truth tables is that we can talk about implication and whether arguments are valid. So for instance, if I say P horseshoe Q and not Q, do those 2 premises entail the conclusion not P? Well, what you would do then is build a truth table and say, well, here we have P and Q, only 4 options, it's pretty straightforward. 4 possibilities, T, T, F, F, T, F, T, F. And then you would somewhere here, you would have P horseshoe Q, you would calculate it. Here you would have not Q, and here you would have not P. Now, if there is no line where the premises of this argument, so these 2, if there is no line where the premises of the argument are true, but the conclusion not P is false, then it's valid, and then the premises imply the conclusion. But if there is a line where P horseshoe Q is true, and where not Q is true, and not P is nevertheless false, if it's possible for the premises to be true and the conclusion false, then it's invalid. Okay? So this is how logic connects up with the notion of validity, which we covered when we analyzed arguments. Okay? All right. Let's see what's next. Okay, some exercises. Okay, well, what's the main connective? Main connective in A, or. Main connective in B, the horseshoe. It happens to be an arrow, that's a typo, it should be a horseshoe. Main connective in 3 is the and. Main connective in 4 is the horseshoe. Okay. Let's do some validity. Let's do just one. Okay. So here we have PQR. I need a lot of space. PQR. And this is the halfway point. And here's the I'm drawing over my own face. Okay, boom, boom, boom. Oh, and then another one like this. So boom. All right. T, 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 F, 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 T, T, F, F. T, T, F, F, T, F, T, F, T, F, T, F. Okay. Now, here we want to do P horseshoe Q. Okay. Here we'll do Q horseshoe R. Here we'll do not P, and here we'll do R or not P. All right, P horseshoe Q. From true to true, true. From true to true, true. From true to false, false. From true to false, false. False to true, true. True, true, true. Q horseshoe R. From true to true, true. From true to false, false. From false to true, true. From false to false, true. From true to true, true. From true to false, false. From false to true, true. From false to false, true. All right, not P is simply the reverse of what P says. So true is false, true is false, true is false, true is false, false is true, false is true, false is true, false is true. All right, and finally we have R or not P. Well, the truth table for or is, well, there's not enough space. Let me try that again. A, B, A or B. The truth table for or is just, it is true as long as one of them is true. So here we have TTFF, TFTF, and then A or B is true when both are true, is true when only A is true, it's true when only B is true, but it's false when both are false. So the or is true on 3 lines. So here we have a disjunction, because that's what you call an or statement. And a disjunction requires for its truth the truth for at least one of the disjuncts. It can be both too, but at least one. Okay, on this line, is R true? Yeah, good. The whole thing is true. On this line, is R true? No. Is not B true? No. Then the whole thing is false. On this line, is R true? Yep. Well, then the whole thing is true. On this line, is R true? No. Is not B true? No. False. On this line, is R true? Yep. On this line, is R true? No. Is not B true? Yes. So it's still true. On this line, is R true? Yep. And on this line, is R true? No. Is not B true? Yeah. So it's still true. So we have a truths except for those 2 lines. Now, the question was, is this valid? So are there any lines where P horseshoe Q is true and Q horseshoe R is true, yet the conclusion is false? Well, here's a line. When are they both true? They're both true here, they're both true here, and they're both true here. And the resulting is also true, right? The conclusion. True here, true there, and true there. So the answer is yep, valid. There is no line where the premises are true and the conclusion false. It's impossible to assign truth values to the atomic letters in such a way that the premises come out true and the conclusion false. So it's valid. Okay, let's move on. Predicate logic. Now, I am aware that many of you found this challenging, and it was because we only had a week. But again, we kept it fairly basic. We didn't do derivations, no inferences, simply translating and checking whether a structure satisfies a formula. So our language is now suddenly very different. Our language is not capital P, capital Q, capital R, but instead we have predicate letters like F and G, and we can make sentences out of these by combining them with logical constants like A and B and C, and you can think of them similar to names like Annie or Billy or Christopher. When we also have relational expressions, for instance, the relation A holds between Annie and Billy. But of course, what's unique about the predicate logic are the universal quantifier and the existential quantifier. Now, the universal quantifier is an upside-down A, and the existential quantifier is a left-to-right mirror image of an E. And whenever you see for all x fx, that is the translation of everything is f. All things are such that they're f. Any x is f. Whereas existential x fx says there is an f. There is at least one f. Whenever you have a predicate letter like f or g, and you combine them with a logical constant, these are closed sentences. These sentences have truth values. You know, if any has the property expressed by f, then f of a is true. But when you combine a predicate letter with a variable like this, f of x, x is not a logical constant. So this is an open sentence. It's impossible to assign a truth value to this particular sentence. But when you combine it with a universal or existential quantifier that binds this variable, now it is a closed sentence, and now the sentence says about all the objects in the domain of quantification that it is f. Okay? Now, we can of course also make slightly more complex sentences, like for instance, for all x, fx and gx. What does that say? Well, it says that everything is both f and g. Everything is f and g. Okay, now suppose I want to say all dogs like bones. And suppose that capital D is expresses the property of being a dog, and liking bones is expressed by the capital L. Initially you might think, oh, well, we can just say all dogs and bones. Everything, all x is a dog and x likes bones. Doesn't that say that all dogs like bones? And the answer is no, because this actually says that everything in the universe is a dog and likes bones, which is not what we want. So we have to scratch that. Instead, we have to say for all x, if x is a dog, then x likes bones. It's conditional. Everything in the domain, in the universe of discourse, is such that if it's a dog, then it likes bones. Okay? Now, we can also combine, of course, these quantifiers with negation. We can say that there exists something, there's an x such that not fx. And maybe there is something that is fx. So this statement says that something is not f and something is f. When you talk about negation and how it connects with quantifiers, there are a few important things to know, which is that you can define the existential in terms of the universal. Well, let me first explain some equivalency. So If I say there's an x such that not fx, that's equivalent to it's not true all x fx. Now why is this true? There's something in the universe that isn't f. There's a counterexample. There's a non-f. Not everything is f. There's one not f. Well, that says the same as it's not true that everything is f, right? If it's not true that everything is f, then there must be a counterexample. There must be something that's not f, which is what is said over here. So there is something not f is the same as saying not everything is f. Okay. If there's suppose that there's an immortal person, f is mortal. Well, then the existence of one immortal person, which is expressed here, there's somebody who's immortal, is equivalent to not everybody is mortal. Okay? And vice versa. If you say for all x not fx, that's equivalent to it's not true that there's an f. You know, if everybody is everybody is immortal. Nobody is mortal. Everybody is immortal. For all x not fx, that is the same as to say there's not a single mortal person. There doesn't exist. It's false that there exists someone mortal. Okay, so this is important to realize how these how negation and the quantifiers interact. Which brings me to my other point, which is that, well, if this is the case, then you can also see that for all x fx is the same as it's not true that there's an x such that not fx. Everybody is mortal is the same as it's not true that there is someone who is immortal. Okay? And similarly, if I say somebody is mortal, I'm saying it's false that for everyone it holds that they are immortal. If someone is mortal, that's the same as saying it's false that everybody is immortal. Okay. Now I anticipate that some of you will be puzzled by that. So the thing about predicate logic is you have to do some you have to get some practice with it before it feels familiar. We will skip the topic of identity. It's not needed. You know, I think one good exercise is similar to the one we did with propositional logic. Identify the main connective. Let's look at some main connectives here. What is the main connective in the first sentence? It's not true that there is an x such that x is h or g. Well, the main connective is not. The brackets show that. What is the main connective in the second formula? Well, this is perhaps a bit of a trick question because the quantifiers also count as main connectives. You know, when the main connective is concerned, you want to know how was the sentence put together? What was the recursive process by which they, or what was the process by which they constructed this sentence? Well, you start with h of x, an open sentence, and g of x, another open sentence, and you create hx or gx, an open sentence, and then you tack on a quantifier with a variable that binds the unbound variables, and you have a closed sentence. So the final operation that was responsible for the construction of the sentence is the existential. So that is the main connective. It's it's the existential. What is the main connective over here? Well, here we see one disjunct, and there's another disjunct. There's an X missing, but or is the main connective, and there the main connective is the horseshoe. Again, the brackets show what the main connectives are in those cases. All right, so this is a little exercise to apply, you're thinking about predicate sentences. So we have three people, A, B, and C. Anna, Bessie, and Caroline. Now, Anna and Bessie live in Northampton, N of A, okay, and N of B. And Caroline lives in Holyoke, H of C. And Anna and Caroline go to the same school. So S is a two-place predicate. It takes A and C. And by the way, every predicate letter has what's called an arity. It's a binary or a tertiary predicate, or a ternary predicate, I think it's called. It has to do with the number of positions that it have to be occupied for it to be a complete sentence. So S is a binary predicate, a relational predicate, a relational expression. Okay. All right. Now let's see if these claims are true in this universe. There is an X such that X has H, okay, and X stands in relation S to A. Okay, so is there somebody in this universe who lives in Holyoke and goes to the same school as Anna? Yeah, namely Caroline, because Caroline lives in Holyoke and Caroline goes to the same school as Anna. And by the way, goes to the same school is you can see that that's a symmetric relationship. Okay, B is a little tricky. B says for all X, HX, horseshoe, SAC. Well, what's the main connective here? It's not the universal, but it's the horseshoe. Well, if it's the horseshoe, we simply have to remind ourselves what is the truth table for the horseshoe. T, T, F, F, T, F, T, F. The horseshoe is true when the antecedent and the consequent are true. It's false when the antecedent is true and the consequent is false. It's true when the antecedent is false and the consequent is true. And it's true when both antecedent and consequent are false. So to make sure that this sentence is true, this conditional statement is true, we have to make sure that, well, as long as this statement doesn't go from true to false, we're good. It's true. Okay, let's first check the consequent. SAC, is that true or false? Well, it's true. It's right there. So this gets T. Well then, but then this horseshoe statement cannot be false, because it's only false when the consequent is false. So we don't even have to check the antecedent. We already know that it's true. True. But for completeness sake, we can check whether this is true, the antecedent. It says everything in the domain is H. Well, we have three people, A, B, and C. Do they all have property H? Do they all live in Holyoke? No, it's false. So basically we are on line 3 of the horseshoe truth table. We go from false to true. Okay? All right, we'll do one more. Forget D. A little too tricky. All right, what does C say? Now we see two quantifiers combined. There's a X and there's a Y. Okay. So you can think of it as saying that there's a pair of individuals, or there's one individual and an individual. They conceivably the same, and one of them has N, and together they go to the same school. Okay. Well, you can think of it this way. Which individuals would you assign to those variables to make this come out true? Is there a person that lives in Northampton and that goes to the same school as some other person in the domain? Well, Anna and Caroline go to the same school. So if we put A here and C there, then the second half is true. And the first half says A lives in Northampton, which is true as well. So this is true. Okay. All right. Let's now try to make formulas false. In fact, let's start with A. Okay. A says there is an X fx and there's a X gx. There's a typo there. Horseshoe, there's an X such that fx and gx. Okay, let's try to clarify what this says. Okay. So what is the main connective? The most important question. Always, what is the main connective? What's the main connective? Really, really essential. I can't think of a more important question when it comes to when you first see a formula in predicate logic. Is the and the main connective? No, it's in brackets. Is maybe some existential quantifier the main connective? No. Is this and? No, it's the horseshoe. The horseshoe is the main connective. There's an antecedent and there's a consequent. Well, the question asks us, try to describe structures in which it's false. Well, if we want to make this thing come out false, and this is a conditional statement, it's a material conditional, we have to find a situation where the antecedent is true and the consequent is false. Because remember, that's what the truth table of horseshoe says. It says TTFF, TF, TF. If you have P here and Q there and P horseshoe Q there, then P horseshoe Q is true, false, true, true. So if we want to make this false, and this is a horseshoe statement, it's a material conditional, we have to try to make the antecedent true, consequent false, because then the whole thing is false. Let's try. All right, so what is the antecedent? Well, that's what's to the left of the horseshoe. Something is F and something is G. Okay, so let's just draw a picture. Here's a universe. Here's an item A, and let's say that F of A holds. And here's another individual. Let's call that individual B, and suppose that G of B holds. And suppose that these are not the same individual. A and B are distinct individuals. have we now made the antecedent of this conditional true? In this particular situation, is it true that something is F? Yeah, A. And that something is G? Yes, B. So it's true that there's an F and there's a G. Of course, we could also simplify it. We could say, oh no, we don't need B. Let's just stick with A and say A is F and A is G. Now the antecedent will also be true because there's an F, namely A, and there's a G, namely A. But now we want to make the consequent false, because our truth table for horseshoe says if you want to make the whole thing false, you have to make the antecedent true and the consequent false. Now, is this false? It says there's an X such that it is F and G. Oh, it's true, because A is both F and G. But we don't want it to be true. We want it to be false. Hold on a moment. Didn't we just have a situation where it was false when we had a B and where B has G? Yes, because now we have an A, which is F, and not G. And here we have a B that's G and not F. But we don't have any object that is both F and G. Okay? A is F but not G. B is G but not F. So now we go from true to false, and then the whole thing is false. So we have succeeded in making the formula false. Okay, let's do one more. Let's do C, for instance. So C says it's not the case that for all y, wy, horseshoe for all y, not wy. What is the main connective? Again, the most important question. Is it the not? No, it is the horseshoe again. Well, we want to make the horseshoe false. That means we want to make the antecedent true and the consequent false. That's our goal. Our goal is to make the antecedent true, consequent false. Let's try that. True, false. All right. Well, what does the antecedent say? It says it's not true that everything is y. Well, a few moments ago I talked about not all having some property is the same as there is something that doesn't have the property. So there's an X such that not Wx is the same as not the case for all y, wy. Okay, so let's invent an individual A, and let's say A is not W. Great. We have satisfied the antecedent. Now we want to make the consequent false. What does the consequence say? It says for all y, not w of y. So not everything is not w. Well, we can again rewrite that using the extension. That just simply means that there is something. Sorry, we have to make it false. So if you want to falsify the claim everything is not w, then you have to create something that is w. So we want to make it false, so we do that. Okay, well, but we don't have something that's w yet, because everything so far is not w. So let's make another individual B, and let's say B has w. All right, so here's our model. We created the world with two individuals in it, A and B. A has not W and B has W. The antecedent is still true, because it's not true that everything is W, because A. The consequent is false, because it's false that everything is not W, because of B. So we have succeeded in creating a conditional with a true antecedent and a false consequent, and so the whole thing is false. And that's what we wanted. Okay. All right. Then the week after that, we covered decision theory. In decision theory, we have matrices where the rows of the matrix are usually decisions, choices, and the vertical columns are usually states of the world. And in some cases, the agent who has to make the choice knows something about the probability of the different states, but sometimes the agent doesn't know that. We looked at some decision procedures. We looked at different strategies for choosing rationally. Now, we wrote numbers in those in the boxes, and that's an outcome, and the number reveals how good the outcome is for the agent. There's different ways of interpreting these numbers. You can think of them as in terms of utility, and of course there are fundamental questions about what utility is and how can it be measured, but you can also think of them as amounts of money, and you can have an agent who has a desire for money, and these numbers could show the extent to which the agent desires those sums of money. Now, some of one of the most fundamental concepts is that of domination, which you also know from game theory. If there's a line, a row, where all the outcomes are at least as high as the outcomes in some other row, and one of them is higher, then that line dominates the other line. That row dominates the other row. So, for instance, if suppose that 8 didn't say 8, but say it said 2. Well, if this were the diagram, then A1 dominates A3, because the outcomes in action A1 are all such that they're at least as good as the corresponding outcome in A3, and at least one of them is even better. In this case, they're all better. But of course, that would make it too simple, so we add 8 to this outcome. Now A1 does not dominate A3, and it doesn't dominate A2 either. Okay, so we saw some principles for deciding. Maxi-min says, look at the minimum outcome for each action and choose the one with the highest minimum outcome. Well, the minimum outcome in A1 is 2. The minimum outcome in A2 is 2. And the minimum outcome is A3 is 1. So here A1 and A2 would be best. Now you might say, well, if there's a tie in how bad the outcome can get, why not look at the second highest outcome? So A1 beats A2 if you're a scaredy cat, right? If you're pessimistic, because the worst outcomes are equally high. That's true, but the second worst for A2 is better than that of A3. So then the highest second worst outcome for A2 is better than A1. And that's called Lexi-min, which is a slightly more sophisticated variant compared to Maxi-min. Maxi-max says you ought to shoot for the moon. Why not be optimistic? So the highest outcome in A1 is 7, the highest outcome in A2 is 5, and the highest outcome in A3 is 8. So the Maxi-max would say go for A3. It's the best. We also saw a view called Optimism Pessimism. Optimism Pessimism says you should look at the best outcome and the worst outcome for each and add them up. So here we have best 7, worst 2, adds up to 9. Best 5, worst 2, adds up to 7. Best 8, worst 1, adds up to 9. So optimism, pessimism would say these are equally good. And by the way, this is a version of optimism and pessimism where both count for 50-50. But you could also, of course, weigh the worst more, let's say 30-70. Or you could weigh the higher outcome more, 80-20. Then we also saw, we looked at a view called min-max regret. And min-max regret says that you ought to look at the different states and calculate how much regret you would have in that outcome. So how do we calculate the regret? Well, suppose you choose A1 and state 1 happens. Then you think to yourself, okay, state 1 happened. I missed out on 2 because I could have gotten 7. So your regret is 2. But of course, if you had chosen A2, there's a typo, that should be 2. Then there would be 0 regret. You did well. If you had chosen A3, then you would have regret level 4. And if you had chosen 2, you would have regret level 5. So you can calculate the regret in that way. 12 is 3 lower than 15. 4 is 9 lower than 15. 15 is 0 lower than 15. 8 is 7 lower. 6 is 3 lower than 9. 3 is 6 lower than 9. 5 is 4 lower than 9. 9 is 0 lower than 9. 13 is 4 lower than 17 is 0 lower than 17. 6 is 9 lower than 17. And 9 is 8 lower than 17. So these are the levels of regret. And min-max regret says that you ought to choose the lowest, highest regret. So let's look at the highest regret for each action. This is 4, the highest regret. This is 9, the highest regret. And this is 9, the highest regret. And this is 8, the highest regret. So the lowest, highest regret is A1. That's how min-max regret works. Okay. Then there is also, of course, the principle of insufficient reason and the principle of maximizing expected utility. The thought is that if you have a decision matrix or a decision, and there are a number of states that could come about, and you have the option between A1 and A2, and you don't know the likelihood of the different states, then absent any indication to the contrary, you can assume they're equally likely. So you would assume that they each have a 1/3 chance of occurring. And of course, if the principle of insufficient reason tells you can conclude that, then you can just start behaving in a way that maximizes expected utility. So if these are the utilities and these are the likelihoods, then you could simply do 1/3 times 6 plus 1/3 times 2 plus 1/3 times 8, and that would give you the expected utility of action A1. But of course, you can only apply expected utility when you know the likelihood of the different outcomes. And the principle of insufficient reason is one way for you to get those likelihoods or those probabilities. Another few concepts we talked about were the concepts of contraction, expansion, and revelation. Now, it's not important for you to memorize those. I will give the formulation, but you have to be able to apply them. And so here's an example where you apply them. This is the exercise we talked about last week. There's a menu of choices, A, B, and C. That's the full menu. Then there are restricted menus, A, B, or A, C. They're sets of options. Now, contraction says, if you choose an item from the big menu, like B, then it would be very strange indeed if you didn't pick B from this limited menu. I mean, if I pick A here, that would be weird. I would say, oh, B beats A and C. But if B is up against A, it doesn't beat A. That's very illogical. Expansion says, if there is a certain option that beats the competition in pairwise contests, then it should also beat the full menu consisting of all those competitors. So let's say that I choose A here and I choose A there. And then I suddenly don't pick A in the full menu. I pick C, say here. That would be weird, because here I'm saying that A can beat B, A can beat C, but suddenly when A is up against B and C at the same time, it no longer beats C. That would be very weird. And here's revelation, which says that if you choose an item when a second item is available, then whenever you choose the second and the first one is available, you should also pick the first. Turns out that revelation does imply both contraction and expansion, but it's not the same. So you can have situations where contraction is satisfied, expansion is satisfied, but revelation is not satisfied. If I recall correctly, number B here is a case where you have contraction. Yeah, because you pick A from the full menu and you pick A in this small menu, but you also pick A in that small menu. So contraction is satisfied. Expansion is also satisfied because there's no option that beats the competition in pairwise contests, but that is not chosen from the full menu, because A beats everybody in pairwise contests, but A is also chosen from the main menu. C does not beat everybody in pairwise contests, and B doesn't beat everybody in pairwise contests. So expansion is also satisfied, but extraction is not satisfied. Sorry, revelation is not satisfied because you pick C from A and C, okay? Now, so you pick C. That means that you pick an item when a second is available. You pick C and A is available. then whenever you choose the second A and C is available, you should also choose C, but you don't in the first line. If you choose C when A is available, then whenever you choose A and C is available, you should choose C. But you don't do that because you don't pick C in the first line. You can make a little mental ranking in your mind and say, okay, if this person picks A and C, that means A and C are equally good. And they pick B from B and C, so B is better than C. And they pick A from A and B, so A is better than B. But how can B be worse than A, and A be equally good as C, and B be better than C? And here we have a cyclic preference, and that's slightly problematic, it seems. That's why we want revelation. Okay. Now the final concepts we talked about in decision theory were the issue of rankings. Like, when are two rankings ordinally equivalent? When are they cardinally equivalent? And when are they ratio scale equivalent? Well, the easiest way to do this is to think of it visually and say, well, if we have two scales and we put one scale along the y-axis and the other one alongside the x-axis, and we put the items on our diagram, on our graph. So suppose I have a top 10 with movies, right? And I have two scales in which I rank these movies. And in one, Godfather gets 1,000 points, and The Big Lebowski gets 800 points, and The Truman Show gets 600 points, and North by Northwest gets 200 points. Actually, that should have to be 2,000, but okay. And in the other scale, that's a scale from 0 to 10. So here it's 10 and 8 and 3 and 2. Well, these scales are ordinally equivalent as long as they preserve the order. And for that to happen, there has to be a line that goes up. It's monotonic increasing. It's just an increasing line. It can go flat as long as it never goes down. It never goes to the right and downward. And then the order is preserved, but nothing beyond that. The size of the intervals is not preserved, going from scale A to scale B and vice versa. The order is preserved, but nothing beyond that. Now then, there are more informative rankings where we also want to preserve the size of the gaps. So the example that I gave in class was Fahrenheit, and here we have Celsius. That's scale B. Well, you can get from the one to the other scale, if there's a difference between two temperatures, right, and the difference is 20 Fahrenheit, and then a little further down the scale we have a gap that's also 20, then you know that the gaps in Celsius must also have the same size. You know, because this is a linear connection between those two scales. if you can draw a straight line through these entries on these two scales, then you preserve the cardinal ranking, and the sizes between the options is preserved. You know, if there's a gap in temperature that's twice as big as an earlier gap interval in temperature, then you'll see that in the Celsius scale or in any cardinally equivalent scale. This is a cardinal ranking. And then there's a special case of the cardinal rankings, which are connected to each other by a straight line going to 0. So if I have the kilometers per hour, and here I have miles per hour, that we know that 100 or 160 kilometers an hour is 100 miles an hour, and 70 is like 70 miles is like 120 kilometers or something, maybe a little less. But we know that 0 miles per hour is 0 kilometers an hour. So these are ratio scale equivalent. And these concepts are important when thinking about utility, because the one question is, how can we measure the extent to which people's desires are satisfied? Is it reasonable to think that we can compare different outcomes for individuals in terms of a cardinal scale or even a ratio scale? Or is that perhaps merely an ordinal scale? Many economists would say you can only measure utility in terms of an ordinal scale. All you know is that some state is better than some other state, but you cannot quantify how much better state A is compared to B than state B is compared to state C. Comparing intervals in terms of levels of desirability doesn't make sense, according to these economists. Okay. So I think these were the most important concepts for decision theory. Then, this past Friday, we were supposed to do probability theory, but we didn't get through it. We didn't get to it because of Corona. So let's talk about these concepts. Probability, I will sometimes use prob or also lowercase p of A. The probability of some statement is at least 0. It can never be negative. Non-negativity. If something is a logical truth or a tautology, it is raining or it is not raining, tautology, then we say the probability is 1. And one of the most important rules when thinking about probability is the probability of P or Q is the probability of P plus that of Q minus that of P and Q. Okay, and you'll see this rule in action in just a moment, and you'll see why this is the way it is. Because when you see it in working, it is very intuitive. Okay. Here are some examples. Here we have 36 marbles, okay? And there's an event going to take place of you grabbing a marble. And we can think about this space in terms of set theory. This is probability space with 36 equally likely most specific outcomes. Okay. There's a sure thing event, which is you grabbing a marble, which is 36 out of 36, it's a sure thing, it's 1, probability 1, it will happen. And there's also the impossible event of you grabbing no marble, 0 out of 36, because it's guaranteed that you will get a marble. All right, so all the probabilities we're interested in are in between those sure thing and the impossible event. And we can just do the math, right? We can look at 36 options, and then we can look at certain events, like the event of grabbing a dark red marble. All right, so the 12 marbles on the left side are dark, the 24 white are light, and then we have a red, the lower half is a red, and the top half is indigo, and most of them are round, but there are 9 square marbles, believe it or not, square marbles. So, what are the chances of grabbing a dark red marble? Well, red is 18, but it also has to be dark. That's only 6. So it's 6 out of 36 equals 1/6. Okay. So yeah, again, we're assuming that every marble is equally likely to get picked. And there's the event of grabbing a dark marble, and that event can be realized in 6 different ways, right? Can grab it, this marble, that marble, that marble, that marble, and so on. All right, what are the chances that your marble is indigo given that it is light? So this is a conditional probability. Probability of indigo given vertical line light. Well, we know that you have grabbed a marble from the right 24. These are the light ones. And then we want to know what is which proportion of those is indigo. Well, that's half. That's 12 out of 24, which is a half, like I said, yeah. What are the chances that your marble is dark given that it is red? Okay, so we have, how many reds do we have? 18 reds. The dark one, there are 6 dark ones over there. So that's 1 in 3. All right, and now we get to this, the rule I just mentioned, the general disjunction rule. What is the likelihood that your marble is indigo or light? Okay, let's think about that. So let's look at all the indigo ones. 18 out of 36. Plus, let's look at all the light ones. That is 24 out of 36. So let's add them up. And then we have 30. Oh, that's 40. What the hell? 42 out of 36. What just happened? It cannot be bigger than 1. This is bigger than 1. Okay, I forgot. I forgot to subtract the probability of both, right? So we have indigo 18, light 24, and then we have to subtract both. So a big bracket and then minus, well, how many are both indigo and light? 12. 12 out of 36 equals, well, everything minus 6, right? So it's 30 out of 36. Right? 42, yeah, exactly. Yeah. Okay. And again, on the exercise sheet, there are some more complicated questions. In fact, let's try to do one of them. For instance, suppose I want to know what are the chances of grabbing a square. So I grab a marble 2 times, and I put it back each time. 2 times a marble, that is square plus dark plus indigo. Okay, well, square, dark, and indigo. Well, there are not too many of those. Only 2. So grabbing a marble 1 time, that's square, dark, and indigo, is 2 out of 36. But to do that twice is to do it to the power of 2. So that is the answer to the question. What's the likelihood of grabbing a marble that's square and indigo and dark twice in a row after putting it back? All right, and here we have some card questions. Well, a deck of cards is 52 cards, 4 suits of 13. Every suit has 9 non-face cards and 4 face cards. The Jack and the Queen and the King and the Queen. All right, so what are the chances of first getting a 5? Well, there are 4 5s in 52 cards. And then I put the card back, and then I pick a heart. Well, there are 13 out of 52 hearts. So we have 2 independent events. We multiply them, and this is the likelihood of B. Look at F, for instance. F says, first we grab the 8 of spades. Well, that's very rare. That's 1 in 52. Then the 3 of diamonds. That's also very rare, 152. And then a black card. Well, that's not so rare. That's half, 26th out of 52. So we multiply these 3 things with each other. All right, so I think that the card business should be doable. All right, and now we come to applications of Bayes' theorem to a number of puzzles or questions. Now, Bayes' theorem is usually written the probability of the hypothesis given the evidence equals the probability of the evidence given the hypothesis times the probability of the hypothesis divided by the probability of the evidence. Now, why is this true? So on the worksheet, there's a little explanation of why this is true, and I mean, you can easily memorize this formula, but it takes like 3 steps to see why it is true. It holds on the basis of the definition of conditional probability, because you can define the conditional probability of H over E, which is the probability of both H and E divided by probability of E. And you can simply rewrite the numerator. You can rewrite it the way it's written here. So it's useful to do the exercise on the handout where we explain why Bayes' theorem holds. But it's also important to apply it, and so here we have a story. The question is, it It's about a car mechanic. The likelihood of a dirty carburetor, given that it produces black exhaust. Okay, so we want to know P, dirty carburetor, D, given that it produces black exhaust. Well, then we want to know, we can calculate it based on the likelihood of black exhaust given a dirty carburetor times the likelihood of a dirty carburetor divided by the likelihood of black exhaust. And here in the story it is 0.9. Probability of D is 0.1, and we divide it by 0.2. Okay, so this is a fairly straightforward application of Bayes' theorem. Sometimes with Bayes' theorem you have to calculate the probability of the hypothesis given the evidence equals probability of evidence given hypothesis times probability hypothesis. Sometimes what's in the denominator, the denominator, I don't even know what it's called, is a little more complicated. Because in many cases we don't know the probability of E, the evidence. And in fact, you have to do the probability of the evidence given the hypothesis times the probability of the hypothesis plus the probability of the evidence given the negation of the hypothesis times the probability of the negation of the hypothesis. So sometimes this is all you have to go on, and so then this is just a more complicated way of writing down the probability of E. And so in some of the examples on the sheets you have to apply this slightly more complicated version of Bayes' formula. But I think that if you apply it a number of times it should be intuitive. Okay. So I think I'll stop here. I've been talking for 2 hours now, and I hope that this lecture was useful. And there's a lady over there coming with a tropical drink, so I'm sitting here on the beach and I'm going to drink a pina colada. So I'll talk to you guys later.